Bueno, muchísimas gracias a todos por su presencia aquí. Un verdadero honor presentar al profesor Grégoire Allaire. Él actualmente es el director del Centro de Matemáticas Aplicadas de la Escuela Politécnica de París. Su carrera científica es bastante extensa. Se ha interesado por numerosos temas de la matemática aplicada a lo largo de su trayectoria, entre ellas la homogenización, los problemas de diseño óptimo de materiales, propagación de ondas, que va a ser uno de los temas sobre los cuales va a hablar en esta oportunidad, los modelos por ecuaciones en derivadas parciales, el análisis numérico y entre otros, digamos, porque sigue la lista de temas en los cuales ha hecho contribuciones notables en matemáticas aplicadas. Tiene escrito sobre todo trabajos de investigación 7 libros, de modo que ha dejado plasmado y concretado su trabajo por escrito. Y lo que es muy importante es, y que ha recibido reconocimiento internacional, es por la interacción que él ha hecho de todos sus trabajos de investigación con la docencia. Yo los invito a entrar en la página web de él, en el cual él muestra los diversos cursos que ha dictado a lo largo de su carrera, y todos ligados en interacción con su trabajo de investigación, y en todos ellos siempre ha introducido innovaciones importantes en cuanto a cómo enseñar tópicos difíciles de la matemática. Hay, por ejemplo, un curso sobre análisis funcional y aplicaciones, que yo lo invito a revisarlo. Hay un curso sobre homogenización, que tampoco es fácil de explicar. Hay cursos sobre análisis numérico de ecuaciones hiperbólicas de leyes de conservación. Está la parte de diseño de estructuras. Bueno, son 8 o 9 cursos que ustedes pueden revisar y que él ha dictado a lo largo de su carrera, y que uno lo nota que están en interacción con sus trabajos de investigación, lo cual uno siempre predica, pero no siempre practica. Uno siempre dice que el trabajo de investigación alimenta el trabajo docente, y que inversamente uno se nutre de mucho de lo que los estudiantes a uno le consultan. Pero yo creo que en el caso de Grégoire es un caso muy emblemático, en donde efectivamente se ha producido perfectamente esta interacción entre los estudiantes y el trabajo de investigación, y que se ha plasmado en 7 libros que reflejan ambas cosas. Su relación con Chile es, yo diría, muy extensa e intensiva. Su primera visita a Chile fue el año 89 para el segundo congreso, o sea, hace 35 años, 89 ahora, 85, 86 años. Segundo congreso franco-chileno, que en ese momento pasó a ser latinoamericano. Primero había sido solo franco-chileno, y en ese momento pasó a ser Congreso Franco-Chileno y Latinoamericano. Él estaba haciendo un postdoctorado en los Estados Unidos y aceptó con mucho gusto venir a visitarnos. Estuvo acá casi una semana, y desde esa época, en estos 35 años, la verdad es que ha sido muy intensa la colaboración en cuanto a cursos que nos ha dictado, seminarios que ha dado, personas que ha formado, que ha recibido en Francia, y colaboración en trabajo de investigación. Las más recientes, veo algunas personas aquí, como el caso de Matías Godoy, que estuvo trabajando con él casi un año o más de un año en la Escuela Politécnica. Está otro de sus colaboradores cercanos, que es Sergio Gutiérrez. Bueno, la verdad es que un tremendo privilegio tenerlo de vuelta en nuestro país, en nuestra comunidad, y bueno, ya forma parte de esta familia, ¿ah? Así que muchas gracias, Grégoire. Y en esta oportunidad nos va a hablar de wave propagation in periodic media, slow light and dispersive effects.
No, this one should work. Huh? Thank you, Carlos. Good afternoon to everybody. Sometimes I'm happy not to understand very well Spanish because I think he said a few words which were maybe a bit too many, too much for me. But okay, thank you very much, Carlos. Indeed, it's a great pleasure to be back in Chile. My first visit was 35 years ago. Wow. Chile has changed a lot, like we did. And I'm going to talk today about some joint work with Maria Pia Palombaro, who is now a professor in Italy at L'Aquila, not very far away from Roma, and Jeffrey Rausch, who is a professor in Ann Arbor University in Michigan, about wave propagation in periodic media. So it's supposed to be a colloquium, so I hope that I have enough pictures so that you can enjoy the topic of this talk. So this is the outline. I will tell you a few words about what is the physics that I'm looking at, and then I'm doing mathematics about it. And I will start with the case of homogeneous media before we go to periodic media. So you will see exactly what is the difference between a homogeneous medium and a periodic medium. And I will talk also about low frequency. Okay. I'm going to talk about light propagation, and this one does not propagate light very well. Huh? Low frequency and then high frequency, and then I will conclude. All right. Anyway, the goal of this talk and this work is to study wave propagation in periodic medium. Why? Why are we going to study wave propagation in periodic medium? Well, actually, because periodic medium are used a lot. Like, for example, here you see the cross-section of an optic fiber. And in the cross-section, you see many holes. And the reason for those holes is that you have a defect in the middle, and this defect will channel the light, and the holes around will force light in some sense to get focused around this circular defect in the middle of the cross-section. There are many possible applications. So those ones are typically what are called photonic crystals, that is crystals in which you propagate light. But you also have phononic crystals, that is crystals with a periodic structure where you propagate sound. Okay. So why are they interesting? Because they are so-called metamaterials with a very strange property. So typically you see this is some kind of glass where you have holes, so you have airs inside. And the property of air and glass are not that much different. But their periodic arrangement give properties which are very different, completely different. And in particular, you see here you have a kind of a line defect in a periodic medium. Here you have this line defect which makes a kind of a branch. And this is exploited. For example, this is some result of numerical simulation, where for some given frequency of light cannot propagate in the periodic medium, and so it follows the channel which has been designed inside this periodic medium. And here you see this junction where you can see a branching of the light. And so defects in a periodic medium can channel waves, and then this may be used. And this is a big project, and I don't know very much about it, but there is an idea of one day to do a light computer. So that's be a computer where you replace electricity by light. What is interest? Light propagates very fast, but it does not dissipate heat as much as electricity, and so could be very interesting to break, the size of smaller and smaller microchip by using light instead of electricity. There is one additional difficulty if you want to build a light computer is how are you going to store information? Memory, you need to have a memory which will not be based on electricity or magnetism, but on light. And so the idea is that you can slow light. Light can be very slow in a periodic medium. So that means that you can almost stop light. And so you can store it. If your signal is made of light, the signal can be stopped, almost stopped. How can it be that you can stop light? How can it be? Well, it is again because you are propagating light in a periodic medium, and I will explain this. But here is an old breaking news in the journal Nature in 1999, and this was in a very specific periodic medium, which is called a Bose-Einstein condensate. So something that you don't see in Nature, right? Because the first Bose-Einstein condensate was observed, you see, recently, just before this publication, and they were able to slow light at a speed of 17 meters per second, while you know that in a vacuum, light propagates at 300,000 kilometers per second, so really very slow, okay? of course, on a very small sample and for very short time. Huh? But this was in something very complicated, and then the next record was a few years later. This was now in a crystal, so that is in a solid material, and they were able to slow down light at 45 meters per second. So that means that, thank you. This one? Ah, I changed the USB, good. So that means that if you can slow down light, you can store it in some specific periodic medium, at least for a few milliseconds or nanoseconds, that will be enough. Yes. Thank you. Yes, good. Slow light. Okay, so being able to slow light is something that I want to explain to you. There is another unusual aspect of propagation of waves in periodic medium, which is called dispersion. So typically on optic fibers, light travels on very long distance. I mean, it's communication between different countries. And then on such long distance, the signals can be deformed. And this is one effect of so-called dispersion, okay? Dispersive effect. And then we need to understand how dispersion appears in periodic medium compared to homogeneous medium. So let me give you a brief explanation of those words that you see very often in light propagation: diffraction and dispersion. You know that diffraction is, if you have a plane wave that arrive on a small hole inside a wall, then the plane waves become different if the hole is small enough compared to the wavelength, and then it's like a circular radial wave, popping up from this small hole inside this wall. So this is called diffraction. Dispersion is something different. Dispersion is associated to this famous experiment of Newton in a triangular piece of glass. If you have white light, then you can decompose it in the different frequency. And the reason is that the speed of propagation depends on the frequency. And of course, you have also the law of, you have the law of refraction at the interface between glass and air that depends on the speed of propagation. And that's why you see a difference between the different type of light, red, green, and blue. Okay, a kind of rigorous definition of dispersion that you find in many textbooks is that dispersion is a measure of how the speed of propagation is depending on the frequency. The frequency is like the color, and then the speed is like the angle of refraction in this case, okay? Well, it's not very rigorous, as we shall see. There are many different possibilities of dispersion, but let's take this one as a rigorous definition for the moment. Another effect of dispersion, if you have a light beam, like my laser beam here, typically it propagates in a fixed direction, but the more you go far away from the source of light, the more it will spread. Okay, even for a laser, I mean, if you look at laser games at night in clouds, for example, you will see that there is a spreading of the laser beam, and this spreading is typically associated to dispersion again. Okay, and I will explain mathematically how you can see that. Good. So the goal of the work is to study homogenization of the wave equation. That is one way of understanding wave propagation in periodic media, to understand this phenomenon of slow light and dispersion, which is different from the case of homogeneous medium. And to make a comparison, let's start with the case of homogeneous media. So homogeneous media, everything I'm going to tell you is very well known, and I'm just taking it out of some textbook. Good. So in an homogeneous media, the wave equation is exactly this equation where you have boiled down all the constant appearing in front of the inertial term or the diffusive term. You have boiled down everything in terms of a C square coefficient, where C is a so-called sound speed or speed of light, okay, depending on the context. And this equation in the full space, well, you have a class of very well-known solutions which are called plane waves, which are simply I omega t, exponential I omega t minus psi x. Psi is a wave vector and omega is a frequency, and they are related. If you plug this formula inside the equation and you want it to be a solution, you get what is called the dispersion relation, relating the wave number, wave vector psi, to the frequency omega. Okay, so that's a very classical thing. And of course, you recognize in the term exponential I psi x something like a Fourier transform. And so with those plane waves, you can build any kind of solution by Fourier analysis. All right, in particular, if you look at a solution which is a traveling wave, so some function v of just one single argument of c dot xi, there is a t missing, sorry, typo here, there is a t missing, plus or minus xi dot x. This is a traveling wave with a speed which is xi divided by, psi divided by modulus of xi multiplied by c. This is a solution of this wave equation. And clearly, you see that plus or minus c is the speed of propagation in this context. All right? Good. And of course, if you vary the wave number xi, you can attain any frequency. That means that any frequency is able to propagate in a homogeneous medium, which will not be the case for periodic media. Okay, so now to understand this concept of slow light and dispersion, we need to look at high frequency. So what does that mean, high frequency? That means that we are looking again at the wave equation, but for specific initial data, where you see that you have what is called an envelope function, V0 and V1. So you have the initial position and the initial velocity of this wave. And those envelope functions are multiplied by a phase factor. This is called a phase factor, exponential I S0 of x divided by epsilon. Epsilon here is a small number, which is a representation of the wavelengths. Right, and you have also a specific scaling of the velocity so that they are of the same order of magnitude. Okay, because what matters is the gradient of the initial position. So the gradient of the initial position should be in pair with initial velocity. So when you take the gradient, you will have a 1 over epsilon that match this one. Okay, so a picture representative of this type of initial data is exactly this. You have this kind of envelope function, and then you have the oscillation that correspond to the phase. That means that the length scale of the oscillation is epsilon here, but then you have this macroscopic modulation which appear in this kind of equation. Okay, and so as I told you, this coefficient S0 of x, possibly varying, is called the phase. Okay, so the idea is to understand what goes when epsilon goes to 0. What happens when epsilon goes to 0? There is a well-known method going back to the 20s, which is called the WKB method for the three physicists, Wenzel, Kramers, and Brillouin, which is also known as geometric optics. So how you go from, in the case of high frequency, from the case of the real wave equation, which is a complicated PDE, to something which is much simpler, which is geometric optics, which is purely geometric. I'm going to explain it. So the idea is, because of the specific type of initial data, we are going to look at an asymptotic expansion, an ansatz of the solution, where you have again this phase, exponential I, of some function of s, t, and x divided by epsilon. This is an unknown function. And then here, because of course this is of modulus 1, you have the amplitude, which is again a power series in terms of epsilon, so u0, the main term in the amplitude, plus epsilon u1, a corrector, and so on. And then what you do is you compute the derivative, time derivative of this asymptotic expansion, the spatial gradient, and then you plug it inside the equation, and you equate several powers of epsilon, and you see what you get. Can you build with this ansatz an approximation of the true solution? And of course, the answer is yes, because if not, I will not tell you this. And of course, because each time you take a derivative in time or space, you get a 1 over epsilon that comes from the phase. The highest order term in this cascade of equation is a term of order 1 over epsilon square, and it is exactly this phase, which is of modulus 1, so it cannot vanish. U0, the first term in the amplitude, so if you assume that you get a solution which is not 0, we are going to assume that U0 is not 0. And then you have the terms that come by differentiating twice the phase, so ds over dt squared. 2 times you have differentiated the phase factor, that gives you a 1 over epsilon squared, minus c squared nabla s squared. And so if you want this ansatz to be valid, this term here must vanish, and so you get, by taking the square root, 2 iconal equations, which are Hamilton-Jacobi equation, propagation equation of order 1, but non-linear because of this absolute value here, that correspond also to the initial data that was in the initial data S0 of x, so the initial phase S0 of x, and you need to solve this. Good. So that gives you the equation for the phase. The next order is an equation which is similar, but now in terms of U1 plus a right-hand side. Okay? But we already know that the phase S cancels this term. So what remains is this is 0. What remains is that on the right, this must be 0 because this term is of modulus non-zero. So this one must be 0. But you already know what is S. Okay? So what you get is more or less a transport equation for U0 or the envelope. You have a transport equation, and the velocity of transport is given in terms of this phase. Okay? Good. Now, let me take a specific, very specific case of what we call monochromatic initial data. So what does that mean? That means that I take an initial phase, which is just a plane wave for a single vector xi dot x, with xi non-zero. Then you can solve the Hamilton-Jacobi equation explicitly, and the solution is very simple. It's simply linear. So the two solutions, remember, you have a plus and a minus for two directions of propagation. The two solutions for the phase are xi x plus c modulus xi times t, or xi x minus c modulus of xi times t. Okay? So very simple phase, very similar to what we introduced as a plane wave solution in my first slide about the wave equation. And then, of course, you plug this formula for S plus or S minus in the transport equation for the amplitude, and you get a velocity, which is exactly c multiplied by xi divided by modulus of xi, which is called the group velocity. And the first information that you get is that this group velocity is actually of the same modulus as c. It is a velocity, so it is a vector. C was just a scalar, but at least you get that, you get that the modulus of V is exactly, again, the value C. So you don't change the velocity of wave propagation when you look at a wave packet at a high frequency. All right, so the conclusion for a monochromatic initial data is that we have built an approximate solution, which is the sum of two waves, one with this phase factor, another one with a phase factor where you change a sign in front of the velocity. And then you have two envelope functions, which are solution of a transport equation, but you have initial data. So you can compute exactly those envelopes. They are determined in terms of the initial position, initial velocity, and they are moving with velocity plus or minus v. Okay, and so the interpretation is very simple. Rays of light propagate in a direction which is given by xi. That's the direction of propagation, right? And it's also the direction of propagation of the envelope of the wave packet. Okay, I don't know if I have again. No, I didn't put again the picture of the wave packet. But not only the oscillation are moving the direction xi, but the envelopes are also going in the direction of this group velocity, which is the same direction. You don't change. Good. We don't see anything about dispersion at this point, and so we need to go to longer times to see something about dispersion, and that's exactly what we are going to do. We are going to look at times of order 1 over epsilon. So we travel for a very long time on a very long distance. So what does that mean? That means that I'm rescaling the time variable. I'm going from t, which was of order 1, now to a new variable epsilon inverse times t. So it's this new time variable when t is 1. This was 1 over epsilon, so a very long time in the previous time variable. So this change of time scale just add an epsilon square term in front of the time derivative here. And because you also have a time derivative here, you get a 1 over epsilon square instead of 1 over epsilon. So it's just time scaling, okay? And the idea is, okay, we know that an approximate solution was with this phase and was traveling with this velocity. So let me make a change of unknown by exactly including this phase and this translation and call the new unknown v epsilon plus, because it corresponds to plus the velocity, instead of the old unknown u epsilon. It's a change of unknown. So let me plug this change of unknown in the equation, and what you get, it's very simple algebra. I put everything independent of epsilon on the left-hand side, and everything dependent on epsilon on the right-hand side, and you see that you have an epsilon term, an epsilon square term. So if you believe that v epsilon plus has a limit, those terms goes to 0. And in the limit, what you get is a new equation, which is not a wave equation, but a Schrödinger equation, right? And of course, I did a change of variable with the velocity, the group velocity plus, and the phase plus. You could do the same with a minus for the other wave, and that will give you a similar result. Okay, and so the result is that we have built a better approximation of the solution of the wave equation, this approximation, I call it W epsilon, you have the phase, you have those two envelope functions, V plus and V minus, which are traveling with the group velocity that we already know. But now the new thing is that V plus and V minus are solution of a Schrödinger equation, not of a wave equation, of a Schrödinger equation. And it's known that Schrödinger equation is a so-called dispersive equation. That means that if you have some initial data, this initial data will be transformed, will oscillate in some sense when time progresses. Okay? Good. And this is a good approximation because the difference between the two goes to zero as epsilon goes to zero. So this is a theorem of Donat-Roch, who did it with a nonlinear equation, so something more complicated. In the case of a linear equation, that's really probably known since a long time ago. And what is interesting is that in this Schrödinger equation, you have a tensor that appears here, and this tensor is exactly the second order derivative with respect to psi of the frequency omega depending on psi. The frequency omega depending on psi is exactly c times modulus of psi, and you get this formula when you compute the second order derivative. Okay, so what is the physical interpretation? Again, the rays are propagating along straight line in the direction of psi, but the envelope functions are deformed because they are solution of this Schrödinger equation, and that's exactly this spreading. If you have something which was really focused at the beginning, it will spread in long time because of this dispersion effect. So that's diffraction dispersion, okay? But what is interesting is that there is no dispersion in the direction of propagation, because if you look at this dispersion tensor, which was inside the Schrödinger equation, it has a kernel, and this kernel is exactly proportional to psi, okay? So that means that in the direction of propagation, you don't have any dispersion. It's laterally that you have dispersion, okay? So that's a well-known fact in the case of an homogeneous media. And again, I recall that the group velocity was exactly the gradient of the time frequency depending on psi. And the group velocity, which is the velocity of the envelope function, is the same, if you want, because it has the same modulus as the small oscillation, right? Good. By the way, because this is a constant modulus, some people claim that there is no dispersion, because, you know, my first definition of dispersion was the effect of varying the frequency on the group velocity. Well, if you simply look at the modulus of the group velocity, nothing changed. But the direction, of course, changed, so actually there is some dispersion. So that's the picture of the wave packet. So again, every small peak here moves with a velocity c, but the envelope moves with a velocity v, which has the same modulus. That's the dispersion again. Okay, so this was the situation for an homogeneous media. Now let's look at what happened in a periodic medium. So here is a picture of a periodic medium, let's say a circular hole in a square cell, repeated by periodicity, okay? And again, I'm looking at the wave equation, but now I have coefficient here in front of the time derivative and inside the diffusion term, okay? So this is, for example, some kind of periodic density if you think about elastodynamics, and this will be some kind of periodic rigidity, if you think about elastodynamics. And so the function rho and A are periodic of period 1, and I scale them with a period epsilon. Of course, I'm going to assume that rho is bounded from below by a positive number, and that A is symmetric, uniformly coercive, and so on and so forth. And I'm looking at some initial data in the right space. Okay, so let me first explain the standard theory of homogenization that correspond to so-called low-frequency data. So what does that mean, low-frequency data? That means that the initial data will not be oscillating with epsilon. So they are smooth. Okay, so I'm just not looking at a wave packet, but just some initial data, which is a smooth function. Okay, and in this case of low-frequency data, homogenization for the wave equation is the same as if I were doing homogenization for a steady-state elliptic equation. There is nothing specific to the fact that you have a wave equation that will be the same formula if it was a steady-state equation, okay? And that's a very classical result, and there is this paper where you have a very nice exposition of the result. So, of course, with the wave equation, you can associate an energy, which is simply the kinetic energy plus elastic energy integrated on the whole space and integrated over time, and this norm, the so-called energy norm, is the one which is a correct norm for talking about convergence. And so the theorem is that if you call rho star the average of the density factor rho of y, if you have a weak convergence of the initial data to u0, so For example, take U0 epsilon equal to U0, not depending on epsilon. If you have a weak convergence of the product of the initial velocity with rho epsilon to some rho star U1, that gives you a definition of U1, then in the energy norm, the solution of the wave equation converges to the solution of this homogenized equation with constant coefficient, right? And the point is that you have this formula for rho star, which is just the average of rho. But for A star, this is the usual homogenized tensor, which is the same if it was a steady state problem without any time dependence, okay? So you don't see any specific evolution effect in this homogenization result. Good. So that's a very nice result if you have initial data which are of low frequency. But let me give you one example where this result does not say anything. This example is if I take U0 epsilon to be epsilon times a function V0, which is depending on the macroscopic variable x, but also periodically oscillating with frequency epsilon. All right? What is the limit, the weak limit of this? This is 0. Nevertheless, it has an H1 norm, which is of order 1, because if you take the gradient of this term, the epsilon is cancelled by the 1 over epsilon. So it has an H1 norm of order 1, but it converges weakly to 0. So the weak limit is 0. You don't learn a lot. And the same for U epsilon 1. Let me take U epsilon 1, the initial velocity. When multiplied by this rho factor, this is some function V1, which is of 0 average with respect to y. So the weak limit of this guy is again 0. So the previous theorem say, well, if this is converging weakly to U0, converging weakly to U1, but the U0 and U1 are 0. So nothing happened, okay? So this result will not be correct for this type of initial data, which are typically high-frequency initial data. Huh? Okay. So we need to understand what happened for this type of initial data, and this is the motivation to talk about high-frequency homogenization. So I'm not going to discuss any kind of initial data, but just very specific initial data, which are made of so-called block waves. So I'm going to recall you what are the block waves. And they are so high-frequency initial data, which have bounded energy. And this initial data will be like wave packets in the case of an homogeneous medium. Okay? Good. So what is a block wave? If you look at this periodic equation where I have rescaled everything to size 1 as the period 1, so you remove epsilon, you have this wave equation. Then there is a family of special solutions which are very similar to the plane wave in the case of an homogeneous medium. But they are not plane waves, they are block waves. So you have exponential I lambda theta of t. So theta is going to be a frequency parameter. It's a so-called block frequency, very similar to the psi, except that it is limited to the unit cell here. Okay, lambda of theta is going to be an eigenvalue for some spectral problem that I'm going to show you in the next slide. Then you have plus 2i pi theta y. So this one is like a Fourier coefficient, but this is a so-called block coefficient in this case. And then you have a periodic function psi of y. What are psi and lambda? Well, they are the solution of a specific spectral problem, which is called Tn here is just the unit cube that I consider as a unit torus. So if you prefer the unit cube with periodic boundary condition, right? And so you look at here, you recognize the tensors, which was your rigidity tensor in the wave equation. You have a dephasing of the, each time you take a derivative in y, you have this additional term plus 2i pi theta, which appears. And then on the right-hand side, you have this eigenvalue, and then you have the coefficient of density rho of y. Why is this so? Well, this is the right problem, because if you multiply psi by this plane wave here, you call it phi, then if psi was the solution of this one, phi is the solution of exactly your equation in the full space. But the problem is that psi has nice boundary condition on a unit cell, while phi, you need to compute it in the full space. Okay, so that's the definition. So far, so good. And what is interesting is that the definition makes sense, because if you take any frequency, block frequency theta in the unit cube, then for this problem, this is a problem with a compact resolvent. So you have a sequence of eigenvalues or normalized eigenfunction of this problem. So you have solution of this problem. Why are we introducing the block decomposition? Because that's the generalization of the Fourier analysis for periodic medium. You remember that in the full space, any function can be decomposed as a Fourier integral, okay? Here you have the same, if you want. Any function u in L2 can be decomposed in a block transformation, a block family. U at which depends both on y and theta, and then u of y is exactly like the Fourier transform, u hat of y and theta multiplied by this plane wave integrated with respect to theta. But, and that's the difference with Fourier, you integrate only on the unit cube, on the unit cell, not on the full space. Of course, there is a price to pay, because if you don't integrate on the full space, the coefficient here, the coefficient here does not depend only on theta, it still depends on y, but it is periodic with respect to y. So more or less, instead of decomposing like Fourier do any function in L2 on a superposition of plane waves, here you decompose any function in L2, any function u, as a superposition of plane waves multiplied by periodic function. Okay? So this is well adapted to equation where you have periodic coefficient, because the periodic coefficient will be transparent for this transformation. Unlike the Fourier analysis, this is an isometry, you have Parseval formula, and so on and so forth. Good. Now that we know about block waves, let me define the initial data I'm looking at. I'm choosing a number, a label for this eigenvalue, let's say n, so the nth eigenvalue, depending on theta, and I assume that it is simple. Then I replace theta by the gradient of the initial phase, and I consider the initial data, which are block wave packets. Okay, so sorry, I thought I have a picture, but exactly like before, instead of having just this oscillation here, I have this oscillation multiplied by this periodic function, which is also oscillating. I have an envelope function u0, and the same for the initial position, envelope function u1, and my block wave, so the solution of my spectral equation corresponding to this eigenvalue. All right? So I'm going to do exactly like in the homogeneous case, but for these specific block wave packets. So again, the WKB method works. And if you want to look how it works, there is this well-known book of Bensoussan, Lyons, Papanicolaou, and there is a single chapter devoted to this WKB method in periodic media. So that's exactly the same ideas, except that the computation are a little bit more involved. Huh? Good. So you make an ansatz of the solution. You see this exponential factor with a phase S depending on t on x divided by epsilon. And here you have the amplitude, which is decomposed now as a sum of a function depending on time, space, but also periodic with respect to the small scale. You compute the derivative of this with respect to t and space x. You inject them in the equation, and you collect terms in different powers of epsilon. And so the first term in this case is the term of order 1 over epsilon, and you get a very strange equation, which is this one. Remember that the operator A is exactly this second order elliptic equation with respect to y, but the theta here is the gradient of your phase. Strange. And here you get that this is equal to 4 pi square rho, the rho which is the density, the varying density, multiplied by ds over dt square times v. And so now you have to think a little bit, because the interpretation of this equation is to say, well, this is an eigenvalue problem, and so this guy here is an eigenvalue. So 4 pi square rho ds over dt square is an eigenvalue. So I claim it should be equal to lambda n of nabla s, and v should be proportional to an eigenfunction. And because the eigenvalue was simple, there is just one single eigenfunction. So you say that v, the v here, is proportional, and the coefficient of proportionality depends on t on x, because this is a PD with respect to y, the fast variable, multiplied by psi n, the block eigenfunction corresponding to this. So you get two information. First, for S, you get an Hamilton-Jacobi equation, a very strange one, but that's an Hamilton-Jacobi equation. ds over dt depends on the nabla S with this very strange implicit function, which is the block eigenvalue. And the second information is that V is proportional to this psi n. Good, okay, so you have two iconal equations here with this initial data. So let me make the story short. The next order term is the same type of equation for V1, but plus a right-hand side. The right-hand side has this complicated formula, forget about it. But you want to solve an eigenvalue problem with a source term. And if you want to do this, there is a compatibility condition. This is so-called Fredholm alternative. You must have that the right-hand side here must be orthogonal to the kernel of this operator, and the kernel of this operator is exactly psi n. So you get this compatibility condition to get a solution. F must be orthogonal to psi n, And when you do the computation, what you end up with will be a transport equation for this V. Let's look at a very specific case, again, monochromatic initial data, like in the case of the homogeneous medium. So I assume that the initial phase was just theta dot x. And then you can compute the solution of the iconal equation. They are explicit, linear in xt. So S plus is theta dot x plus the square root of the block eigenvalue times t, the same for S minus with a minus sign. And then the compatibility conditions, the Freedom alternatives that give you a transport equation, you can compute everything explicitly, and you end up with a group velocity, which is given by this formula. So there is some computation here. Believe me, you get this group velocity. So something very different from the homogeneous case. Okay. Conclusion. Well, we have an approximate solution for my wave equation, this phase, this block wave, and then those envelope function, and the envelope function are transported with this group velocity v, and so they depend on the initial data like this. And again, I can look at longer time and give a more precise interpretation. And so what is this more precise interpretation? Well, I'm scaling time again to get time which are of order 1 over epsilon. So you see the epsilon square term in front of the inertial term corresponding to this change of time scale. And I'm looking again at those initial data, and I'm going to give you a very precise approximate solution in this case. So let me recall that my initial data are determined in terms of a choice of the nth block eigenvalue, lambda n of theta, which I assume to be simple. Because it is simple, it is differentiable with respect to theta, and then we define a certain number of objects. First, the frequency. The frequency is just the square root of this eigenvalue. Okay? Then you have the group velocity. The group velocity is a derivative with respect to this frequency depending on theta, the derivative with respect to theta. And then there will be a dispersion tensor, which is a second order Asian matrix of this frequency omega n of theta. Okay? So that's the objects that are going to appear in my homogenized limit. And so the theorem is the following. We have an approximate solution. U epsilon is a true solution. The approximation is here, and then you have a remainder term. The remainder term is going to 0 as epsilon goes to 0. This approximate solution, this is my block wave here. I have the two phase factor plus and minus 1. I have envelope function v plus and v minus, which are traveling with this group velocity rescaled by epsilon because I'm looking at very long time. Okay? And the v plus and the v minus are solution again of a Schrödinger homogenized equation, like in the homogeneous case. But the dispersion tensor here, remember, is a second order derivative of the eigenvalue lambda n of theta. What is the interpretation? Let me recall the result in the case of an homogeneous medium. And I tell you, in an homogeneous medium, the block transformation is exactly Fourier analysis. There is nothing new in this case. And as I told you, in the homogeneous medium, the frequency was exactly C, I forget the C here, C multiplied by modulus of psi. The group velocity was this one, and the dispersion tensor was this one. And there was no dispersion in the longitudinal direction. In the case of a periodic medium, omega n theta, the frequency is the square root of the eigenvalue. The group velocity is the derivative with respect to this to the block parameter theta of this frequency, and the dispersion tensor is a second order derivative of omega n of theta. Now, I didn't tell you, or this was written in small characters, but this eigenvalue lambda n of theta, theta is in the unit cell, it's periodic with respect to theta. So a periodic function, it does not blow up, it's smooth, right? It has minima and maxima. So if it is differentiable at those minima and maxima, the derivative is 0. So that means that you can tune the choice of theta so that the group velocity is 0, because this derivative must vanish for a periodic function. You must have minima and maxima. So you can choose the theta so that the group velocity vanish. And that's exactly the explanation of the slow light. Okay, and the explanation is that you can choose your frequency so that the frequency is bouncing in your periodic cell and can never propagate, can never travel. Okay, this is impossible, of course, in a homogeneous medium, because in an homogeneous medium, the group velocity has always modulus c. This is not the case here. And then, of course, imagine that you have chosen a theta corresponding to a minimum of omega n of theta. If this minimum is non-degenerate, the second order tensor is going to be positive definite. So that means that A star is going to be positive definite, so of full rank, while in a homogeneous medium, it is always of rank n-1. There is no dispersion in the direction of propagation. Here, there will be dispersion, there will be additional dispersion in the direction of propagation. So completely different. So that means that dispersion effects are more important in photonic crystal than in homogeneous. So again, that's my picture of the same picture of a block wave packet, but you have to imagine that the velocity of each spike is the speed of light, right? So they are bouncing, but the group velocity is at the speed of the envelope function may be 0 if you have chosen a very nicely the block frequency theta. Okay, so I'm not going to talk about the proof. It's going to be too long, but there are two proofs. Either we build an infinite order asymptotic expansion by using a lot of smoothness of the initial data, but you could also just use weak convergence analysis. And so the idea is, as usual, in this type of problem, you have a priori estimate, you pass to the limit, you use clever test function, and then you deduce strong convergence. Okay, I guess the details of the proof are not very important. Okay, so there are some generalization, and I'm very pleased to cite at least one generalization that I done with Luis Fritz, who is a professor here in Chile at University del Biobío. Huh? Yes. So a first generalization is that it works even if you have, the fact that the coefficients were purely periodic was crucial. But you can add some small modulation. The modulation is of order epsilon square, and this modulation can depend on time on the macroscopic variable. But the fact that it is purely periodic is absolutely crucial because block waves work for perfectly periodic media. Good. Then if you look at a case which is not purely periodic, but modulated by X, we don't know the full answer. But under some specific assumption that I don't want to detail here, this is by work with Fritz. So with specific assumption here, you can, instead of having something propagating, you can have something that will concentrate, localize, very similar to Anderson localization, actually. And then, of course, everything that we did with Schrödinger, with a wave equation can be done with a Schrödinger equation or with Maxwell equation up to some modification and some technicalities, but that's more or less the same idea. And so let me cite the two papers where you can find those results in details. Thank you very much for your attention. You're not obliged to, but you can.
You're approximating the wave equation.
Sí, pero no se escucha.
Yes. Very good point. Very good point. Yes, of course. So U epsilon was a solution of a wave equation with a finite speed of propagation, and you end up with something which has, for the envelope function, an infinite speed of propagation, right? But of course, there is a remainder term, right? And so you see that this estimate here is not in a H1 norm, and so that's exactly, you change, the right norm for the wave equation will be the energy norm, and here my error is not in the energy norm, it's wrong, the energy norm for sure, and that's the explanation. In some sense, I'm cheating. You see, I'm using an error estimate in the norm which is not the natural one for the wave equation. But you're absolutely right. You have an infinite speed of propagation for V plus and V minus. Right.
Okay. Do you have Sergio?
Oh, elastodynamic for sure. Okay, for sure. I mean, the fact that it is a scalar wave equation does not matter that much. Okay. But there is a trick, and this trick is, yes, this trick is here. Everything works because I assume that I have an eigenvalue which is simple. So I choose a simple eigenvalue. And so for a scalar equation, you can tell me, are you sure there exists at least one eigenvalue which is simple? And the answer is yes. At the bottom of the spectrum, the first eigenvalue is simple because you have a maximum principle, a Klein-Rothman theorem that tells you this is the case. For a system of equation like the elasticity, we don't know. I mean, by numerical simulation, you find a lot of simple eigenvalue, but there is no serious proof that you can find one. And so, of course, you could prove the same theorem by saying, assume that there is a single eigenvalue. Yes.
Assume that you could have like a sequence of eigenvalues that are simple.
Sorry, if you have a sequence of eigenvalues?
Like if you have considered the radial case and then have like a sequence of eigenvalues that you have all spectra.
No, I don't know what to say, how to answer this. No, I never thought about the radial case.
Okay.
No. One thing, yeah, very good point. Anyway, the two questions of Sergio and yours are very interesting because you see that even if you had a system, right, but you assume that you have a single equation, which is single eigenvalue, which is simple, then if you look at the form of the homogenized equation, you see that the tensor here is a second order tensor. So that means that even if you started from an equation which was a system, let's say, with p unknown, in the end, you get a single unknown. So that means that maybe psi n will be u epsilon and psi n will be vector valued, but the v plus and the v minus will be a scalar envelope. So because of this assumption, you see that the homogenized problem is not the same as the original problem. Not only it's not the wave equation, it's a Schrödinger equation, but it's also not the same number of unknowns, right? It's going to be a scalar equation because I assume that the eigenvalue was simple. And then, I mean, of course, you could say, well, why don't you assume that the eigenvalue is double or, because then you will get maybe a system of two unknowns. Yeah, but then the question of differentiability of multiple eigenvalues are very subtle, and there are probably other effects which are not taken into account in this world. I mean, as soon as you have a multiple eigenvalue, crossings of bounds, many very subtleties, which has been studied by some people, by the way, but not by me.
Is there any other question, comment? What about the nonlinear case, nonlinear wave equations?
Very good. I don't know. I mean, in the case of an homogeneous medium, there are some work, definitely. I mean, this work of Donat and Roche were exactly looking at the nonlinear wave equation in a homogeneous medium. So, but for periodicity, I don't know.
Okay. If there is no more comments or questions,
Another thing, I am not able to follow your but in other fields there are the quasi-periodic conditions,
yes,
quasi-crystal, what happens?
Okay, so that's a very interesting point. So people have studied a kind of a generalization of block waves for quasi-periodic, almost periodic, or random, stationary, ergodic. Let me cite at least one work of my colleague in Paris, Antoine Gloria. So the idea is, the definition of block waves is really linked to periodicity. So how can you define block waves if you don't have periodicity, quasi-periodicity or stochastic? So he said, well, there is this parameter theta in the block waves, and if you are interested in the bottom of the spectrum, so for theta close to 0, you can do a Taylor expansion. And so you do a Taylor expansion. Of course, each term of the Taylor expansion is a solution of a spatial equation. But then for this equation, the fact that you have periodic boundary condition is not important. And so his idea was to say, I cannot define block waves, so I'm going to define the Taylor expansion terms of the block wave, because then I can forget about the periodic boundary condition. And so he has a construction of a Taylor expansion of block waves for quasi-periodic medium or stochastic medium. But not for this specific problem, but for problem of wave propagation, yes. Very recent result, less than 10 years ago.
Okay, so we thank again the speaker. Están todos invitados a un cóctel post seminario, en el quinto piso, en el quinto, no en el sexto, ¿no? Perfecto.